Hey guys, how's it going today? So we're gonna talk about the second bit of the projectile motion section, assuming our PowerPoint decides to work. Hopefully we'll get through the video real quick. That way it doesn't take too much time. So instead of just looking at projectile motion in 2D, now we're gonna look at projectile motion launched at an angle. So in other words, what we're talking about is we are launched at some angle that is not a 0-degree horizontal. So looking at our example here, or our graph, so we have a projectile launched at the angle theta above the horizontal, and it has an initial velocity of vi. So just like we did with previously in last week's lesson, we are going to break this into components. So our x component, just like before, is going to have the same velocity. It's going to be a constant velocity. And because we know that we have a triangle with a set theta, and we know vi, we can calculate what vx is using our cosine of theta equals our adjacent over our hypotenuse, rearrange our equation. So we're going to multiply by vi, and that gives me vi times cosine of theta is going to give me my v sub x. So whenever we're talking about our y component is a little bit more tricky. If we're talking about our initial y component, we have vy sub I, so that's our initial. That's going to be equal to our vi, so my initial velocity at that angle theta. So we're going to use our sine because it's going to be our opposite over hypotenuse. So sine theta equals my opposite over hypotenuse, which would be vy initial over our v initial. So we multiply by vi again, we end up with v. That is going to be equal to vi sine theta. So just jumping back to this chart real quick. So I realize that we see that our vy sub I is right here. We can literally move this and transpose it right here so we make our triangle. So we also know that due to gravity, we would expect whatever this object is to fall with respect to gravity. In this case, we're going to call that acceleration due to gravity a sub y. Thus, we can look at previous known equations and essentially derive equations for the situation. So we know our final vy can be vi sine theta plus ay delta t. We also can go back to that vf squared equals vi squared equation. So instead we have vy sub f squared equals vi squared times sine theta squared plus 2ay delta y. And then we have delta y equals vi sine theta times delta t plus 1/2 a sub y times delta t squared. So all those equations should look relatively familiar to you. So let's take a look at an example problem. So this is the example in your book if it makes it easier to follow along with. Excuse me. So we have a zookeeper finds an escaped monkey hanging from a light pole. Aiming her tranquilizer gun at the monkey, she nails 10 meters from the light pole, which is 5.00 meters high. Tip of her gun is 1 meter above the ground. So at the same moment that the monkey drops a banana, the zookeeper shoots. If the dart travels at 50.0 meters per second, will the dart hit the monkey, the banana, or neither one? So we need to examine this here. So for our problem setup, notice that we have this dotted line, which shows that, the black dotted line, which shows that the zookeeper's gun is being shot from 1 meter above the ground, which means the difference between the monkey and the ground would be 5 meters, but because we're shooting 1 meter above the ground, we're actually looking at a difference of 4 meters. We know the monkey drops a banana, and obviously the tranquilizer gun was shot at angle theta. So, first thing we need to do is figure out what the initial velocity is. We know our x and y components of our triangle. Our x component being 10 meters, our y component being 4 meters, which means we can calculate what theta is. So, calculate theta using tangent, so theta is going to be equal to our arctangent or inverse tangent of 4 divided by 10. We end up with 21.8 degrees. From there, we have to figure out a kinematic equation to solve for our time. So in this case, we're going to use delta x equals vi cosine theta delta t. So we isolate delta t, and then we plug in numbers. We end up with delta t equals 2.15 seconds. Which, if we just take a rough look at what we know the speed is, we know Dart's traveling 50 miles per hour. We're 10 meters away. That's roughly 1/5. So that matches up. So from there, we need to figure out how far each object is going to fall during time. So both for the banana and the dart. So we're going to use our free fall kinematic equation for both. So delta yb equals 1/2 ay times delta t squared. So we have 1/2 times negative 9.81 meters per second squared times our time squared. Ends up telling us that our banana has fallen 2.27 meters, or our displacement of delta y over this time is negative 0.227 meters. Our dart has an initial vertical component, velocity equal to vi sine theta. So we see that we can use delta y is going to be equal to vi sine theta delta t plus 1/2 ay times delta t squared. So plug in numbers, we end up with 3.99 minus our 0.227 meters. We end up with delta r change in y is going to be 3.76 meters. And note that displacement change is 3.76 meters above that original position of 1 meter. So it'd put us at 4.76 meters. So, whereas the other one, we're taking our 5 meters and subtracting our change in displacement, leaving us with 4.76. So our monkey's still up at 5 meters, so we're obviously not hitting the monkey, which means that we are going to end up hitting the banana with our tranquilizer dart. And there's a slight difference due to rounding. So for our assignments today, you guys are going to work on practice E and the section 2 review. The majority of you guys haven't turned in section D yet, or practice D yet, so make sure you get that done as well.